I'll just give it a few more minutes. We're still missing a few people.
Christian was telling me he was stuck in traffic.
Christian was? All right. Do you know when he'll potentially get here, or not at all?
Maybe in a few minutes. I think it was like 10 minutes ago he was telling me
Okay.
that. Yeah, like 4:48 he was like, he'd be 5 to 10 minutes late.
Mm-hmm.
Maybe like 10 minutes from now.
No worries. All right. Can I write on this? Because I don't want to open this up in PowerPoint. Freeform? I don't know what this is. How's it going?
Good, how are you?
Doing well, thanks. All right. And again, I think all of the text is messed up because I forgot my notes at home, so yeah, whatever. I will just do this and present it from this. All right, so last class we basically finished our main discussion of torsion and learned how to basically analyze statically indeterminate and composite torsion structures. Basically, we just kind of realized that everything is basically just all of the same principles that we have just been applying, just now using different constants in order to approximate it for torsion. So they're synonymous to the axial loads, that axial loading equations that we had seen previously. And then afterwards, we went into plastic deformations and plastic analyses for torsional rods, where basically the total torque that is obviously felt within a rod is entirely dependent on the stress distribution that's felt within the rod itself. So, for example, for a fully yielded cross-section, which is basically just from the center of the rod to point C, we found that the torque that is assumed for full plasticity is roughly 4/3 times the torque that gets calculated if we use just a straight up linear elastic stress distribution, increasing basically from 0 to the yield stress. So we learned that basically that the capacity that a rod can really handle can go upwards to about 4/3 or increases by about 33% if you assume full yielding of basically every point from the radius of 0 all the way to the outside radius C. All right. And then, of course, the development of the plastic zone will actually increase further and further outwards, starting from the outermost region, because that's where the maximum stress occurs. And then yielding will just obviously result in a redirection of stresses as you increase more and more load. The yield stress, this maximum stress will just kind of plateau to the yield stress. All right. And then, of course, we derived equations for calculating the torque with respect to the angle of twist, and the relationship between the angle of twist and the angle of twist that would cause yielding. This ratio ultimately allows us to be able to develop a plot, which in turn shows us that the torque that's felt is about linear up until the yield point, and then it behaves inverse cubically once you pass the yield point. And then, of course, if you were to unload it, then we end up with residual stresses and permanent deformations. Again, very similar to if you were to unload an axially loaded bar, it would just behave very similarly. All right. So we had a numerical example. I was too lazy to go through it last class. So today we'll go over it, and then towards the end we'll try and squeeze in a little bit of what is most likely, or most definitely, I will say, my favorite chapter in all of structural mechanics, which I will announce that in a little bit. So for this numerical example, we're dealing with an elastoplastic shaft of radius 5 centimeters and a total length of around 1 meter. The applied torque at the end is specified to be 35 kilonewton meters and eventually then gets released. All right. We're given some material properties, including the shear modulus being 200 gigapascals and a maximum shear yield stress of 150 megapascals. And we're basically asked to determine A, the yield torque, or the torque that would ultimately cause yielding, the plastic torque, which is the torque that ultimately the rod can fully handle before every part of that rod yields, and then the size of the elastic core, which is basically just entirely dependent on what the angle of twist is, and then the permanent twist and residual stresses. So we recall for the torque that causes yielding, this is basically this condition here. When we have the elastic up to the initial yield point, we calculated that the torque at yielding is pi over 2 times the outermost radius cubed times the allowable times the yielding shear stress. And so when we plug all of the variables in, we end up with 1/2 times pi times the 150 megapascals times the maximum radius of 5 centimeters. You would plug in those values and obviously do all of your appropriate unit conversions, and you would get that the torque at which yielding occurs is 29.45 kilonewton meters. The derivation is just very similar to what we had previously seen in class. So I would say, like, pretty much it's just kind of like a plug and chug problem at this point because we had already derived that expression. From here, we ask if for the plastic torque, to calculate that, we basically need to calculate what the torque would be assuming full yielding of the cross section. So what we need to do is integrate from the shear stress times the area multiplied by its radial position. So in other words, just integrating over force times perpendicular distance. We end up with a double integral where it's just an integration of the radial position with respect to the angular position times the radial position. And what we end up with is a plastic torque equaling 2/3 pi times the yield stress times the maximum radius cubed. And what we end up with is a stress equaling or not a stress, but a plastic torque equaling 39.27 kilonewton meters. Now, has this fully yielded yet? No. The reason being is because when we are dealing with a fully yielded cross-section, no, this should be fully yielded. I believe that's an incorrect note, because it should have fully yielded by then. No. Right, it hasn't fully yielded yet. So think of it like this. TP is basically the capacity at which the rod can handle, all right? So previously we had made an assumption about, all right, our rod will start to yield at 29.45 kilonewton meters, all right? Now, if we're considering basically full plastification, then the rod can handle 39.27 kilonewton meters. The problem specified that our torque is 35 kilonewton meters, which is less than 39.27. So we're off by about 4.27 kilonewton meters, which means that there is a plastic core that ultimately develops where the section where there's basically a section that hasn't reached yielding yet. Does that make sense? So from there, what we need to do is we can calculate what the radius at which yielding would initially develop, or the point where we're still within linear elasticity. All right. What we need to ultimately do is take an integral, and this integral is basically going to be a function of the radius and also the existing radius at which yielding will start to occur. Now, what we're trying to figure out is sigma y. So this section here of the integration, we just break this stress integral into two parts, all right? The first part is just going to be the area underneath the curve here for the linear elastic region, which is sigma times sigma over sigma y times tau y. That is just basically just relating the ratio of whatever the existing stress is along some coordinate point here to the total radial yield stress. What this ultimately is, just think of it kind of like a triangle. You're breaking it up into two parts. Another way to think of it would be if you were taking some of the moments and then you took moments about point O of the triangular part, and then you did some of the moments of that rectangular part. That's basically what's going on here. All right? It's just the calculus is obviously making things a lot more complicated, I think, than it honestly needs to be. So it's just sum of the moments, and the total integral is just the triangular part here plus the square part on the outer side, for which is full yielding. All right? So from there, the integration basically gets solved, and what we end up with is we set the total torque equal to our existing 35 kilonewton meters, which is the torque that is obviously applied to the rod. And then you can basically just back calculate the yielding radius, rho y, and we end up with that radius equaling 3.788 centimeters. Does anyone have any questions up to that point so far? Everyone understands that, I'm going to try and draw it over here, that we're going to have a linear elastic region up until this point, and then it's going to plateau here. So the total area that's basically underneath here is just going to equal rho times some ratio rho y, tau y dA. where that dA is basically just a function of the radial position, right? D rho, d theta. And then basically what this is just doing is just allowing us to basically sum it for points, like if we were interested in a point here, or a point here, or a point here, we need to have that ratio in order to account for the variation in the stresses. That's ultimately what it's doing. Are there any questions about this? No? All good to continue? All right. Now, the last part of the problem is just basically asking to calculate the permanent twist and the residual stress. So, to calculate the elastic twist, we first need to just ultimately calculate what the angle of twist due to the torque in the core is. So this is basically the angle of twist that is existing for the elastic portion of our core. So that's the portion that's still behaving to linear elasticity. So this just comes from TL over GJ because, again, this follows linear elasticity, so we can just apply our equation that we had previously derived from way early on in chapter 3. And what we end up with is a total rotation of around 1.13 degrees. And where this rotation is occurring is directly at this point here. All right? From there, what we have to do is then account for the angle of twist that would be occurring due to the presence of the maximum shear stress. And what we end up with is calculating that the angle of twist will end up being around negative 1.02 degrees. Because again, we basically just need to apply superposition for the angle of twist that would ultimately cause that same rotation. So it's just kind of doing a reverse calculation to basically compute what the equivalent stress would be that would cause that type of reverse twist, just accounting for now that rectangular portion. So, and then from there, we just end up with a summation of the two angle of twists. The residual is just basically, if you think about it, it's like this triangular portion here. So that angle of twist total would contribute to about 0.11 degrees. Are there any questions about this at all? Andres, are you raising your hand? All right. All right, and then the residual twist. That just basically, once you figure out what the maximum stress is, assuming a linear distribution, just going the opposite direction, it's just a summation of the two. And you would just find that the maximum angle, that the residual stresses are just the difference between whatever the yield stress is and whatever you would calculate as a kind of, it's not a real stress, like this tau max here, like that's not obviously an actual stress, but it does behave according to linear elasticity. So it's just going to obviously be a difference. That's ultimately how plasticity is kind of characterized, is through the definition of residual stresses, which is basically just whatever the stress is according to linear elasticity that exceeds the yield stress, minus whatever the yield stress is. So it's basically just how much more is the yield stress, is the actual stress over the yield stress. Does that make sense? Basically, the stress, if we kind of ignored linear elasticity, and we just, not ignore linear elasticity, but if we ignore plasticity and we just use straight up linear elasticity, we would calculate that the stress at the outermost part is 178.3. Obviously, you can't get a stress of 178.3 because we yield at 150. And so because of that, you just have to take a difference. And that's when you end up with your residual stresses. Does that make sense? That's what I was trying to explain. Sorry. All right. And so just as kind of like a recap, we have linear elastic behavior. where our stresses and strain equations are basically synonymous to everything that we have seen so far for axial loading. The stress is basically just equal to the shear modulus times the shear strain. The shear stress is equal to whatever torque multiplied by the radial position at the point of interest divided by your polar moment of inertia. The screen went off. That's never happened before, I don't think. There we go. And then the torque is equal to basically just a summation of all of the stresses times their areas times their radial positions. And then you can use Hooke's law to obviously derive expressions relating the angle of twist to an associated torque. And then we further emphasized on plastic behavior and analyzing how plasticity comes into play and how to analyze a structure assuming some type of yielding criteria. All right. Now the last section is basically just talking about failure under torsion. Basically, it's assumed that once you basically achieve a maximum normal stress, so this is basically, think of it like Mohr circle for the problem, we have to perform stress transformations in order to calculate the maximum shear and normal stresses. In this case, the normal stress that's felt along some perpendicular face or face of interest is basically at a 45-degree angle from whatever maximum shear stress is being experienced by the torque. Now, this is assuming that the torque is the only applied load in this case. You can also have cases where it's combined torque and axial loading or even bending in those cases, in which case then you would need to characterize tau xy, tau xz, tau yz, and then do like what we did early on in chapter 7 using Mohr circle like 2D and 3D principles to calculate the normal and shear stresses. But as long as it's obviously not within a plastic region, you can observe all of the linear elastic regions. It's just the trick becomes just applying which stress to which. All right. And then lastly, just so you guys kind of see how a shearing failure would look. For a ductile failure, we would see that the material for ductile behavior, ductile meaning that it behaves very close to linear elastic, and it's a ductile material would be something like steel, for example. We'll see that the material will fail directly along some given shear plane. But for more brittle materials, this could be something like like an aluminum, for example. That'll have a more brittle failure, which means that the normal stresses will generally govern that type of failure mode. So ultimately, it just goes down to, again, using stress transformations, understanding how the material will fail, and then understanding what failure criterion you would want to use in order to understand which failure. Failure criterion, I don't really think we went too much into it for Chapter 7 because that's usually a more advanced topic in engineering mechanics. So you guys will definitely learn about that more in the future as you advance with your studies. For example, there's like more Coulomb failure criterion, there's von Mises stress criterion. I know this sounds very worrisome and such, but believe it or not, probably half of you are using it for your design projects without even realizing it. All right. Are there any questions about anything relating to torque or torsion or anything before I go into my last chapter, which is chapter 11, strain energy?
There was a portion of this that you said was not going to be on the test. It was the plastic, right?
Plasticity is not going to be on the exam. I may give it on the... Wait, did I give the torsion homework already? No, I think it's out already.
Oh, yeah.
Okay.
The next one.
Then yeah. So basically, no, I don't plan on giving it on the exam because it's kind of like a special topics thing. I would say focus more on the linear elasticity, and then of course, I'm still trying to decide if I want to give you guys the true-false questions. No? That would be the only instance where I may give questions about the plasticity, where it's not necessarily a calculation-based question, but more like a theoretical-based question.
I want
You want them?
Yeah.
All right, we got one. All right,
Just give it to him.
just give it to him.
Yeah, I'll take them.
All right.
With them high.
Maybe I'll give them as bonus questions, right? Where for each question you get right, you get 1 point on your exam, up to a total of 10 points towards your final. Make sense? You want that? All right, I'll do that then.
But like no deductions. If
Yeah.
you have-
No, but here's going to be the catch. With the bonus questions, I'm going to make it semester-wide.
Okay.
All right, so I can ask anything. So I can ask stuff about bending. I could ask stuff as simple as chapter 1, statics, because we did that as a review. I could ask anything about like special topics questions. So I would say, don't worry. Yeah.
We're not having like a cumulative final, or we still having that as well?
There's no cumulative final. The final exam, exam 3, is just basically going to be chapters 9, 10, and chapter 3. And then I'm going to give like bonus questions. Like those are going to be the true false questions. Each one going to be an additional point if you get it correct. And that is basically going to be every single chapter, even including the chapter 11 questions that I'm going to include here.
So there's not going to be anything chapter 11 wise other than the true and false? Because on the syllabus it says 9, 10, 3, and 11 for exam 3.
Okay, then yeah, I'll put chapter 11 on the exam. Thanks for the reminder.
Okay.
All right. Strain energy. All right. Any other questions about torsion before I show you guys the absolute beauty / nightmare? You will either love it or you will hate it. All right? Because it can be a little confusing. Any questions? Chapter 3 at all? No? All right. To the nightmare. Let me open this up in PowerPoint. All right. So, strain energy. Strain energy is one of my, if not my favorite topic in this entire class. Basically, everything that we have been dealing with so far has included Hooke's law, right? Force is equal to some spring constant, or as we derived it as just stiffness, for whether it be axially loaded stiffnesses, bending stiffnesses, so on and so forth, where the stiffnesses are dependent on material and geometric properties. In a similar way, we can actually solve problems using a different approach. If you guys remember from, I think, Physics 1, you learned 2 different ways to be able to solve problems. That was just with force methods to analyze problems. And then you also had energy methods to solve problems. And you can use either or to be able to solve for problems and end up with the same answer. We can do the exact same thing here. All right? As you guys should hopefully recall from Physics 1, that the work is equal to the area underneath the force displacement curve for a spring, for example, right? So here we would have a force displacement curve. It would observe linear elasticity, but in some instances it doesn't observe linear elasticity. For example, if you were dealing with plasticity, either way, you would be able to use energy methods in order to determine associated displacements. All right? As we should hopefully recall, that the work that is basically the force times the distance is equal to just the area underneath that curve for nonlinear cases, which is just the integral of the force curve times dx. That should be p, actually. This should be p. So that's already a mistake. All right. So this is where we ultimately start off with for our strain energy. All right. In the case of linear elasticity, we get a nice linear curve. where the work can just simply be calculated as the area of that triangle, which is 1/2 times the force times the displacement that is experienced. And then obviously the slope of this curve here is equal to K, the stiffness of a given material. In a very similar way, we had already seen this using Hooke's law, but for stress strain, where the slope was the elastic modulus. So it's a very similar concept, all right? Now, how do we go about using energy, all right? Well, what we first need to consider is equilibrium and energy conservation. What this means is that the external energy that's felt in a system has to equal the internal energy within a system. If you guys recall, for force equilibrium, the sum of the forces and sum of the moments equals 0 has to be observed for both internal and external equilibrium. So we can apply the same concept to energy, where the total energy for the external system has to equal the internal system. And then this can be broken up into strain potential energy and kinetic energy. However, in a lot of instances, when we are dealing with structural systems, do you want your buildings to move? No. So, for a lot of the problems we will be dealing with, we're going to say that the kinetic energy is equal to 0. Now, if you're designing something like an airplane or something that moves that needs to be able to handle static and dynamic forces, that kinetic energy term is no longer 0. Our course will not be delving into that. There are more advanced and even graduate level courses that focus on that. All right? So, in doing this, we assume that the structure should be static and that the work is just straight up equal to the potential energy or the strain energy. Now, as we recall, from our linear elasticity, the work that is felt for a given structure is equal to 1/2 times the force times its associated deformation, 1/2 P times delta. Now, for multiple forces, in the case of, for example, a stepped rod or whatever, it's just a summation of all of those forces times their associated displacements. All right? And that is equal to the internal strain energy. We expand on this a bit more and write our terms in terms of stress and strain. So force is equal to stress times area, and deformation is equal to strain times length. And we ultimately get that the total external work is equal to 1/2 times stress times strain times the volume of a given solid, because again, everything has 3 dimensions. And hence we get a general solution for the internal potential energy, which is equal to 1/2 times the integral of stress times strain over the volume of a given solid. Are there any questions about anything that we have seen thus far? No? All right. Now, this is great and all, but there's a lot of cases where we can have different types of loading. We can have bending loading, torsional loading, and so on and so forth. So what we should do is maybe derive some expressions to be able to calculate the potential strain energy for different types of loading. That is what I did here. Let's consider an axially loaded bar with some non-uniform cross-sectional area A. All right? We should recall that the strain is equal to the differential of the deformation divided by, with respect to x. And that stress is just equal to E times epsilon from Hooke's law. And we end up with that stress is just equal to E times d delta over dx. Next, we recall the definition for axial force, which is the integration of the stress times the area. We replace our stress term with the term that we derived above. E is equal to d delta times dx. And then we, of course, integrate that with respect to dA. And then lastly, we can kind of throw everything into the stress equation and the strain equation. So knowing that stress is equal to E d delta over dx, and strain is just equal to d delta over dx, we end up with our strain energy, sigma times epsilon, equaling E d delta over dx, d delta over dx, which is how we end up with that term there. 1/2 times E times the differential of the deformation with respect to x squared, all integrated with respect to the volume. The volume is going to be a triple integral over the x, y, and z coordinates. And what we end up with is just a potential energy equation equaling just E times d delta over dx squared times dx times dA. All right? And this is the general case if you have a non-uniform cross-sectional area. Now, in practice, for very simple structures, guess what? The area is constant. So we can then replace our terms, and what we end up with is a strain energy equation equaling the axial force equation, or the internal force of a structure, divided by EA. We integrate that with respect to x, and we should ultimately be able to calculate the strain energy in the problem. Now we can do the derivation for many other types of problems, including bending, shear, and torque, and you would ultimately find that the equations are, again, just synonymous with one another. So for example, for axial loading, we derived this equation here, where the axial force divided by EA is, how do I erase? I can't remember how to erase. Let me just go back. ENS, there, whatever. So, anyways, for axial loading, we need to basically determine the axial internal force equation to derive what the internal force would be with respect to x. In cases where you have like a point load, for example, n of x is just going to equal some uniform constant n. For bending, you would have m of x squared is divided by EI. M of x, of course, is not as simple as n of x because beams subjected to transverse loading that are not pure bending will obviously always be a function of x. This is what we learned in chapters 4, 5, and 6. We could derive the same expressions for direct shear and, of course, torsion. And ultimately, the only thing that really changes are just the constants, which those constants are what we had seen in all previous chapters. All right, so I'd like to actually really quickly do an example, just because I haven't really gone into, I just want to kind of show you guys what we would do. All right, so I want to just really quickly draw out a nice little figure, because I did not prepare one, but I did prepare a problem just before class. All right, so let's consider a beam with some force P, and it has dimensions of A and B over a total length L, and X is defined as being from the left-hand support. All right? So the first step to solving this problem would ultimately be to first understand which strain energy equation we want to use. For this type of loading, which strain energy equation do you guys think we should be using? Bending. General case of bending. All right. So we get that U is equal to 1/2 times the integral over the x coordinate times m of x squared over EI dx. All right. Now for this problem, we're going to assume that EI is just some constant, right? So this could be like a W shape, for example. Yeah. All right. And so we can actually integrate by carrying that EI out of the integral. All right. From here, we obviously need to know what the bending moment is. So, to determine the bending moment, we need to draw out the bending moment diagram. Does anyone know how the bending moment diagram will look? You just have to tell me how it looks, all right? I'll give you guys the answer. If you guys can tell me how the bending moment diagram will look, I would be so happy. Christian.
Isn't it like it's gonna go up like linearly to the point and then decrease down afterwards?
Exactly. So our diagram is just going to look like this. If our reference fiber is on the bottom, then we are dealing with positive bending. Let me just make this really nice and neat. All right, so that's right. Where the maximum bending moment would just be at the location where the force is applied, in this case. All right, now the values of these equations, we would have MA of x, or the bending moment within that region of 0 to A. That would just equal P times B times x divided by L. For MB of x, which is from 0, which is less than x, or which is less than b, this is going to equal P times A divided by L times B minus x.
So what does the first one say? I cannot.
Oh, PB times x divided by L. And then the maximum bending moment is equal to PAB divided by L. Any questions so far? Hopefully everyone should be very familiar with how to determine the bending moment diagrams. You know, you guys can do a sanity check on me if you want. It's correct. All right. So, what do we do from here? Well, we have two bending moment equations, but our strain energy expression is only per bending moment equation. So technically, what we're going to have is two U's. One for the region 0 to A, and then one for the region 0 to B. And that is going to be the total strain energy within the system. All right? So, U is just going to equal 1 divided by 2 times EI. That gets carried out of both integrals that we're going to write down. And what we're going to end up with is an integral with respect to x, which is just going to be technically the bounds 0 to A of MA of x squared, which is just going to be PB over L times x squared dx plus the integral from 0 to b of PA over L times b minus x squared dx. Then the tricky part is just doing all the math. All right, so let me copy and paste this. And just erase all of this. So from here, we just work out the math. So that first integral is just going to equal 1 over 2 EI. And then this entire integral is just equal to the integral from 0 to a of p squared b squared x squared divided by EI L squared, all with respect to dx, plus the integral from 0 to b of p squared a squared times b minus x squared divided by EI L squared with respect to dx.
Why did you include EI again if you took it out?
Good point, sorry. I'm low-key following part of my notes, but yeah, EI should be factored out. All right, so then you would just solve for these integrals. So you get 1 over 2 EI. The first integral is just going to be p squared b squared over L squared times x cubed divided by 3, and that is bounded from 0 to a, plus p squared a squared divided by L squared times negative b minus x cubed divided by 3 from 0 to b. Solving for all of this, you would just get that the total strain energy within the system is equal to p squared a squared b squared divided by 6EI over L. Just real quick. Just because I see something, but I just want to make sure that I'm right with it. Yeah, all right. So that's the total strain energy within the system. Now, what if we wanted to find the deflection at the point? All right, what's one method that you guys learned about how to calculate deflections? Double integrating each of the bending moment equations, and then it just gets annoying, solving for all the constants. Well, we just derived the strain energy expression. What is strain energy equal to? Strain energy is the internal work, right? What does internal work have to equal? External work. What was the expression for external work?
W is equal to U or what?
What was it?
Never.
No, say it again. I didn't hear you.
No, you just gave us W is equal to U. I don't know what the other one was.
What was W equal to?
1/2 force times deformation, or 1/2 stress times area times E times L.
1/2 P times delta will do. Yeah.
Mm.
Well, from here, let's let W equal U. We get 1/2 P times delta is equal to P squared A squared B squared divided by 6EIL. The p cancels out with one of the p squared terms. The half can cancel, so that becomes 3. And what we end up with is delta is equal to pa squared b squared over 3 EIL.
Delta being deflected.
The total deflection, the vertical deflection. So this would be y in the deflection equation case. All right? Now I invite all of you to look at figure 8 on this packet here. And just look at what the deflection would be at the point of the load. I have 2 of these packets here. No, I do not. Never mind. Let me see. Yeah, no, I don't have
Looking at deflection on what?
the deflection at the point of the load. Notice how it matches? That's just a standardized table of deflection equations. So ultimately we get that delta is equal to pa squared b squared over 3 EIL. Now, this is the deflection at the point of the load, not the deflection at which is the maximum deflection occurs. So it's a very powerful tool that can be used to find deflections at a given location where a load is applied, all without having to do double integration. Do you guys like this better than double integration or no? You think this is better? There's just one limitation to it. The fact that it can't always give you the maximum deflection. All right? It'll only give you the deflection at the point you're interested in. Now, there's a nice workaround to it. All right? And that is called the principle of virtual work. But actually, before I do that, I want to show you guys another example. So the principle of virtual work, that's my personal favorite one because it is so powerful that you can basically calculate deflections of anything at any given point. Yeah, for example, like we didn't learn how to calculate deflections of a truss or anything. You can find out nodal position changes of trusses. So you could figure out what the deflection of a truss is if you knew how to do it, which I'll show you guys probably next class because the problem takes a little while because you have to solve for each member. All right? So before we go into the principle of virtual work, I just want to do one more example just to really show you guys how this equation would work. All right? So let's consider a fixed point. And let's consider a force P. In this case, it's actually going to be relatively simple because guess what? The load is going to be applied directly where the maximum deflection occurs. So in this case, we'll be able to actually find out where the max deflection is. So in this case, if the load had been applied directly at the center, then we're given the maximum deflection. All right? So this deflection, this beam is located at a point L with a coordinate x. All right? Now we can draw the bending moment equation. If we set our reference fiber to the bottom, then what we end up with is a negative bending moment equation where our value... Thank you. This moment would be negative PL, and then m of x would equal P times x minus L. All right? Again, let's use strain energy to calculate 1/2 times the integral of 0 to L of m of x squared divided by EI times dx. You end up with 1/2 times the integral of 0 to L of P times x minus L the whole thing gets squared divided by EI dx. We, instead of having to calculate what the strain energy is, you can just kind of enforce W is equal to U already. So it just kind of removes a step. And what we get is 1/2 P delta is just equal to 1/2 times P squared divided by EI times the integral of 0 to L of x minus L squared dx. We can see the halves cancel, one of the p's cancel. So we calculate delta is equal to P divided by EI times x minus L cubed divided by 3 from 0 to L, which gives us delta max because that's where the load is applied, where the point where the maximum deflection will occur. PL cubed divided by 3EI. Any questions about this? I think I want to do one more example, which I'm just going to come up with off the top of my head. But in this case, instead of it being for bending, I'll probably make it for axial loading, which should be so much simpler. All right, so let's consider a fixed rod here. I forgot to mention that EI should be constant in this problem. That's an important distinction. And in this case here, for the axially loaded rod, this is a force P subjected to a length L and a coordinate position X. Now, what was the strain energy equation for an axially loaded rod? Yeah,
N squared times L over 2EA.
exactly. Now, this case becomes very simple because our n value, if we were to draw n of x, so that's our diagram, our n of x term is just going to be constant at p, which means that basically n is equal to p. So because n of x is a constant p, then the equation simplifies to just n squared L over 2EA. In the instance of when n of x is non-constant, would be something like a traction force, if you guys have heard of that before. A good example to think of what a traction force might look like would be if you have a piece of rebar in like concrete. The concrete grips every point of the bar. So technically the force at the very ends of the bar is 0, with the force increasing as you go closer and closer to the center of the bar, at least until it yields. All right, so just plugging in U, and we get P squared L divided by 2EA. And then simply put, if we wanted to find the deflection, W is equal to 1/2 P times delta. Setting W equal to U, you just simply end up with delta is equal to PL divided by EA, which is just our expression. Now I want to do something a little bit more challenging. I want to try an axial member subjected to attraction force. So this is P of x, and I want to set this equal to 4, I'll just call it W. All right. Now, who can tell me what the diagram would look like at this point? Anyone? Yeah.
Is it a slope upwards?
Yeah. Well, so basically we would get a reaction force here, which would just equal W times L, right? And so we would have, that should be blue, WL at the top, and then it slopes down to 0. So then N of x is just equal to W times L minus x. All right. Now from here, we can calculate the strain energy, 1/2 times the integral from 0 to L of W times L minus x squared divided by E times A dx. All right. From here, it goes to 1/2 times W squared over EA times the integral from 0 to L of L minus x squared dx. Let me write EA equals constant there, just so that way it's defined. So W squared divided by 2EA times negative L minus x cubed divided by 3 from 0 to L. And what we end up with is W squared L cubed divided by 6EA from the looks of it. Someone correct me if I'm mistaken. If you guys can fact check me on that. All right. Now, what if we wanted to find the max displacement at the free end? Now it's a little confusing, right? What would the total work be? Well, we would still have 1/2. What's the total force?
Would it just be the area underneath that diagram?
Not the... Would it be... Yes. I'm trying... No, because the total force would just be WL. It's the...
Yeah.
Yeah. W times L, and then delta is just the deformation at the free end. All right. So, setting W equal to U, we end up with 1 WL over 2 delta is equal to W squared L cubed over 6EA. The W's would cancel, one of the L's would cancel, and then the 2 would cancel, so that would become 3. So delta is equal to WL squared divided by 3EA is what I get. So now it's a different type of expression for a more complicated load. Any questions about this at all? Any of the examples that we had previously covered?
Can you explain where you got the WL again when you did 1/2 times?
Yeah, so the work is equal to 1/2 P times delta, P being the total force that's applied externally, and then delta being whatever deformation is caused by that external force. Now, the total external force is just the magnitude of the distributed load, W, times the length. All right? Now, this problem is not just explicitly limited to 1/2 P times A. I do want to make some adjustments now that I'm thinking about it really quickly. All right? In the same way that for linear elasticity, we have this force displacement curve. You guys would agree with me that for a given moment, for example, like at a fixed end, there's an associated rotation, right? That's, if you guys think about from chapter 9, compatibility, the rotation at a fixed end has to be 0, which means there's a given moment. So because of that, we can synonymously replace this P with some given moment, and then X with some given rotation. So we can also technically have an expression for work equaling 1/2 M times theta. And then, of course, all of our U expressions would just be the same. Make sense? So let's do a quick example using this one right here. I'm actually going to throw this right in the middle here. And in this case, we have, oh, did I just erase the whole answer? Yeah, all right. All right, in this case, we would have 1/2 M theta is equal to P over EA. P over EI times X minus L cubed, right? And that integration would still kind of follow. But in this case now, M would just equal P times L. So we have, let me check something just to be sure. It doesn't give me it. So 1/2 times P times L times theta. The magnitude of this, I think, was, well, this would still be P squared. That, the 2's would cancel. P here would cancel with that, so we end up with L theta. And then what we end up with should just be equal to L theta equaling PL cubed over 3EI, which means that theta is just equal to PL squared over 3EI. Make sense? Everyone understand why the moment would just equal P times L, right? All right. All right, so I think with those examples kind of like covered and out of the way, I think I'm probably just going to leave it here today, just because strain energy, it's a very similar concept, but from what I recall, everyone struggles with the concept of a quote-unquote virtual force and virtual displacement, even though mathematically it's about the same. So if you guys have questions, feel free to let me know. Otherwise, we'll continue our discussion of strain and energy next Monday. All right? Cool. Yes, calculation reports are due Monday. Wait, when is the Monday? When is
Wednesday.
Wednesday, the 13th?
A week from now.
It's whatever the 13th is. I can't think straight.
1 week.
Yeah. How are the projects coming along?
I haven't worked on it since Monday.
You haven't worked on it since Monday?
Yeah.
Hope you get it done.
I have a stupid question. Is there a difference between a capital buffer and a working cylinder?
It's
On
preference.
the sheet, yeah, it's capital.
It's preference. Like they assign a bunch of different things. Like in chapter 9, we use y to represent deflection. You know, that's why like in a lot of like codes, for example, they usually have a key of like labels. So, yeah.
Yeah, it's just capital.
Mm-hmm.
But it still means the same thing.
Yeah, as long as it's clearly defined as, you know, being the deformation, which, you know, I'm familiar with a lot of different ways to categorize it, so I'm not gonna like be annoying about it. Have a good one.
Could you go over the virtual energy and displacement?
Virtual?
Yeah.
Right now?
Like, what did you? I was a little confused on what you meant on virtual.
Basically,
I offered up my shit.
the external work done by the virtual forces on the real displacement needs to equal internal work done by the virtual stresses on a real displacement. It's a very confusing topic.
They now want to.
But it's
out of nowhere.
basically like imagine two entirely separate systems and then merging them together, where your virtual system is basically like a unit force, unit displacement type of thing. And then it's kind of like a scaling situation to get the alignment to properly work out. You'll see that everything will work out at the end. It's the concept of virtual forces and virtual displacements. It's not an actual force that's being applied, but it's like a kind of like characteristic or dummy force, for example, that would be applied. That's actually how you would be able to find deformations at any given point. And what you would actually find is that the expressions are entirely similar to what we had previously defined. Just now one is characteristic of the virtual location. So it's basically like here, you know how I said that the displacement would basically be computed at the point where the load is applied?
Yeah.
By doing it this way, it's not limited to that, because then you can have a load applied here, but then you can figure out the displacement at that point, as long as you apply a load there. The trick, though, is then you technically have to solve two problems in order to get that, you know? And so for those instances,
But I'm just saying, like,
in some instances, it may be easier to do double integration, but for very complicated problems, you want to do this because it'll just speed up the process tenfold from having to do double integration, especially if you have like a frame with like 40 different members. You could just do strain energy, principal of virtual forces or displacements and figure out either the force or the deformation at a given point, depending on the type of analysis that you're conducting.
Oh, okay.
we did.
Yeah.
And is that in the
That's basically what the
Textbook
connection is.
or-
I just added little notches.
That I'm
so
not
you're
sure.
You know, so it's not sliding.
I'm not sure. Because this is like, I know, principle of virtual forces and displacements. It's a very advanced topic, but I like to cover it because it's more broad and it's very similar. And we are actually making really good pace this semester because nobody's asked me a ton of questions or to go over a bunch of different things. So.
That would be more than enough.